In Chapter 16, we're going to explore beyond our solar system. Look at some of the stranger things that are out there in our universe. The learning objectives here, I'm not going to take the time to go through all of these individually, but you definitely should, because they will help you to focus your study efforts. If this flashes by too fast, remember the PowerPoint notes will be on Canvas for you to view, download, print at your convenience. And the narrated version here is just to go a little bit deeper into the subject matter that maybe you won't understand if you're just looking at the PowerPoints. Cosmology is the study of the universe, not to be confused with cosmetology. Those are two different things. The universe's structure, its properties, how it began, how it will end. A lot of this is based on physics. A lot of it is based on mathematical models. So it's a huge undertaking to figure out what's going on in this vast universe that we have. Well, we know it's a vast universe now, but for the longest time, we didn't. After the Copernican theory was widely accepted, people still thought that there was only one galaxy, and that was the one that the Earth was in. They could see the stars in our galaxy, but they could also see some fuzzy patches, but they were thought to be nebula. And as you know, nebula are clouds of dust and gas. But in the 1700s, there was a German philosopher that came along by the name of Immanuel Kant, who kind of threw a wrench in the works, because he proposed that maybe those fuzzy patches were galaxies, just like the Milky Way is a galaxy. And maybe they could contain billions of stars. And he called these fuzzy patches island universes. Well, there wasn't much acceptance of this idea, because that would make Earth insignificant. So you had this debate going on between whether it was a smaller universe or whether it was a larger universe consisting of more galaxies than just the Milky Way. And this debate went on. That debate continued until Edwin Hubble enters the picture. In 1919, he took a job at the Mount Wilson Observatory, which is located outside of Pasadena, California. It's still there, still famous. And at that observatory, at the time, was the world's largest and most advanced telescope. So his goal then was to solve the mystery of those fuzzy patches. Were they nebula or were they galaxies? And Hubble had been studying a class of objects called Cepheid variables. Cepheid variables are types of stars that pulsate regularly as they're rotating. And as they rotate, there are variations in diameter and temperature that produce changes in the brightness. But that regular cycle is a very well-defined cycle. Very well defined, stable period of amplitude and temperature. So the absolute magnitude then can be calculated by knowing the rate at which they pulsate. And you might think, well, why is that important? He was looking at the absolute magnitude compared to the observed brightness. So why does that become important? Because a reliable distance can be calculated. And distance is all important in the study of the universe, because we want to know how far away things are. And light from these things is one of the major ways that we're able to do that. So this is what we're talking about. This is the pulsating nature of these Cepheid variables. There will be a low period of low luminosity and then a high period, and that happens in a time frame or in an interval that can be calculated. And there's the highest amplitude, here's the lowest amplitude, and it's a very regular basis. And here's Edwin Hubble. Most images that you see of him, he's smoking a pipe, and here he is with that very large telescope. Well, Hubble found one of these Cepheid variables embedded in those fuzzy patches when he turned the telescope at Mount Wilson to those fuzzy patches. So the bright stars appeared very faint to Hubble, so he realized that they had to lie outside the Milky Way. And he calculated that the fuzzy patch was more than 2 million light years away. Well, we know today that that is the Andromeda galaxy. That's the nearest galaxy to our Milky Way. So Hubble's discovery was not insignificant. It was a huge event because it expanded our knowledge of the universe, and it also expanded our universe into a bigger universe. Neil deGrasse Tyson has a book called Death by Black Hole, and in that book he explained that discovery as not only were we not in the center of things, but overnight our entire Milky Way galaxy, the last measure of our self-worth, shrank to an insignificant smudge in a multi-billion universe that's vastly larger than anyone had previously imagined. Since knowing distances is pretty key to figuring out the characteristics of objects out there in the universe, let's take a closer look at methods to do that. The first one that we'll talk about is stellar parallax, and you know this one from Tycho Brahe's work. Remember, he didn't think that it was a heliocentric universe or solar system because he couldn't measure stellar parallax, and he figured if the Earth moved, he should be able to measure it. But one key thing that he didn't know was that stars are just too far away, and he didn't have instruments that he needed that could measure the angles that were that tiny. The farther away something is, the tinier the angles are going to be. This is showing an example here of where we've measured something. We've made observations in February, and we've made observations in August, and we've sighted on the Pleiades, which is a constellation. And then we look at how our view changes. What are the background objects here? How does that change? And just using some trigonometry then, we can figure out the distance if we know those angles. So stellar parallax is one way. The further away the object is, the smaller that angle. So here on Earth, with our ground-based instruments, most stars, I think there are only about 100 stars that we can get stellar parallax for, but luckily we have space-based instruments that can measure the parallax of many more stars. And then the second way is what Edwin Hubble used, standard candles, those class of astrophysical objects such as supernova or the Cepheid variables that have a known luminosity due to some characteristic quality that they have. Type 1a supernova, they will always have the same amount of energy associated with them for some reason. Then the other way is the light year. That's the distance that light travels in a year, and that's 6 trillion miles or 10 trillion kilometers. So looking at the stars or other objects that we can view because of their brightness or because of the light, the electromagnetic energy that they emit, is like looking into a time machine. When Hubble calculated the fuzzy patch that was 2 million miles away, 2 million light years away, he was seeing it as it looked 2 million years ago because that's how long it took that light to get to Earth. So when we see something that's 60 light years away, we're seeing it as it was 60 years ago. One of the things that I like to talk about is Betelgeuse. Betelgeuse is a super red giant in the constellation Orion, and it's about 800 light years away from us. Well, this might have Betelgeuse, and I probably won't be able to spell that right, Betelgeuse, something like that, might have already gone supernova, but we don't know it because the light from that event hasn't reached us yet. So why is it important to know the distance to objects? Well, First of all, it allows for learning what the luminosity is. How bright is something? And that's very important to know because we can understand how big it is, how much energy it is emitting. We can also determine what the masses of objects are from their orbital motions. And we can find out, we can calculate the true motion through space of stars. Are stars moving in space? You bet they are. They're not just stuck up there like the underlit surface of a bowl over us. They are actually moving away, and we can also learn what the physical sizes are of the objects that we're looking at as long as we know the distance to them. Today we know that the observable universe is thought to contain 200 billion galaxies, and each of those galaxies contain hundreds of billions of stars. Think about that number for a minute. Your book describes this as there are more stars in our universe than there are grains of sand on all the beaches on Earth. That is mind-boggling. That's just a staggering number. That's why, there has to be some other life forms out there, because there are just so many chances that life could exist. Maybe extremophiles, maybe not extremophiles. We also know today that our universe is 13.8 billion years old. How old is our solar system? 4.567 giga-annum, billion years old. So our universe is much older than our solar system is. How do we know this? We know this because we study the oldest light. The oldest light should have been there at the very beginning, and that oldest light has calmed down considerably, so it's cosmic background radiation. It's not visible light, it's microwave radiation, and we've measured that, and we've measured the age of it. That was the radiation that was produced during the Big Bang. The Big Bang, probably not an explosion. It was a singularity where all mass, all energy, everything that we know was concentrated in something smaller than the head of a pin, and it turned into everything that we know today. All atoms, everything was formed at that point. Impossibly high densities, impossibly high temperatures, not even atoms could exist at the time, but the conditions were there for atoms to form later. Things had to cool down considerably in order for these strange particles that were moving around to sort themselves out into actual atoms. So finally, we get the universe that we observe today from all that 13.8 billion years later. So just a reminder, a light year is the distance that light travels in a year, and it's 10 trillion kilometers or 6 million miles. This is an image showing the birth of our universe from that singularity and as it expanded into the cosmos that we know today. So our universe started out as a singularity. A singularity is this tiny pinpoint of infinite density where nothing like we have any experience of. The concepts of space and time have no meaning here. But it inflated over the next 13.8 billion years into the observable universe that we have today. We can't peer back to the birth, but we do have that echo of the Big Bang in the cosmic background radiation. So we can use that and kind of wind backwards to see how that might have occurred. And the only thing that we can come up with is that there was a singularity that birthed our universe. What was there before? Good question. Who knows? But in the first second after the Big Bang, the surrounding temperature was about 10 billion degrees Fahrenheit. That is incomprehensible. But not even atoms could exist in temperatures like that. But there was this soup of all of these subatomic particles with these weird names like quarks leptons. There was antimatter present. Luckily, matter outweighed antimatter, or nothing would have ever happened because everything would have been destroyed. There were bosons. These were what protons eventually formed from, but it was too hot at that point for that to happen. So then we get to this point called the Dark Ages, and that lasted for several 100 million years. No stars were forming at that particular point. Then about 400 million years after the Big Bang, the first stars began to form, and from those stars we end up with galaxies forming and planets forming around in those galaxies. Then we now know, because of some work that was done by astrophysicists around the world, but a few of them were at Cal Berkeley, we know that from those supernovae that our universe has accelerated in its expansion. And the only explanation that they can come up with is a new form of energy that we have no idea what it is. And that's why it's called dark energy. So from that, there we go. Here we are today. Just to give you some idea of just how mind-boggling large our universe is, I wanted to show you this image from Hubble. This is called the Hubble Extreme Deep Field, and it was made by combining 10 years of images from the Hubble Space Telescope. And it's this one part of the sky near a constellation, which its name is neither here nor there, that astronomers had always been interested in because it was an empty patch. So the size of that empty patch, if you just look up at a full moon and you see the diameter of that full moon, that's about the size of that empty patch. Astronomers had always been interested because they couldn't see anything there. When all those images were compiled from Hubble, this is the result. In this image, there are over 5,500 galaxies. Every little tiny point that you see here is a galaxy, except for a couple of points. This one being one right here, that's a star, and you can see the points from the star. I think there's another one somewhere, but I don't see it right now. So these show galaxies in every stage of their development. The large fuzzy red galaxies where there are no new stars that are being formed. And then you see the spiral pinwheel galaxies like the Milky Way and like Andromeda. You see some of those here. And all of these tiny little dots back here, those are the galaxies that are the faintest and most distant galaxies that have ever been seen. This peers 13.2 billion years back into our universe. So the farthest galaxies away are 13.2 billion light years away from us. So if we've got that in a little empty patch of our sky, then it's, as I said, I can't think of any other way to just mind-numbingly crazy of the number of galaxies that we could have out there. And remember, galaxies contain hundreds of billions of stars, and who knows how many planets there could be. And this is our Milky Way galaxy. Our Milky Way is still an active galaxy, still in the process of making stars. Our solar system is located out here in one of these spiral arms called the local or Orion arm. So here we are, and we're out way in the countryside of our galaxy. If we were located closer toward where all of this activity is, nighttime would be as bright as day because of all that we would be looking up at all of these stars at night. And then here's another view of it. It's a beautiful pinwheel galaxy. I might be biased, but I think the pinwheel galaxies are the prettiest of them all. And if you go out at night on a nice clear night, you can get an idea of our Milky Way. It's called the Milky Way because it looks like milk that's splashed across the sky. And that's the galaxy that we live in.